Hello friends, welcome to our YouTube channel. In this series of basic process engineering calculations, we will today focus on the how to calculate the max pressure rise in a reactor due to blocked vent. As a process engineer, I guess you are came across many of the situation where you have to calculate the maximum pressure rise due to generation of any of the vapors that may be due to thionyl chloride or HCl or whatever may be the vapor composition, and that contribute to the rise in pressure in case of vent block. Today I just elaborate you how to calculate the max pressure rise in such a case situations with one of the example. Today we will just consider one of the example where we have two intermediates that we add to form a product, and the byproduct is the HCl. So first, reaction mixture 1, the reaction mixture 1 and reaction mixture 2, we have two reaction mixtures, and the reaction mixture 1 contains the limiting reagents. Here we assume that the 10,000 kg of material 1 and the 3131 kg of material 2. Okay, so density of reaction material 1 and the same is density of the reaction material 2. As we know how to calculate the pressure rise, in this case we have to follow the equation of ideal gas law, and to follow that we need some data. So we just input the density of the materials in kg per meter cube for the both of the material. Then we need to calculate number of moles based on the molecular weight. So molecular weight of reaction mixture 1 and molecular weight of reaction mixture 2. Okay, here we have to get the data of molecular weight of reaction mixture 1 and the another is reaction mixture 2. Okay, so then we have, as I already discussed, we can calculate based on the limiting reagent. So quantity of limiting reactant in reaction mixture 1. Okay, so we have x kg of limiting reagents. Then we have to calculate the max pressure rise for the whatever the reaction time. So here we take time of operation is the 2 hours. Okay, you can consider as per the your process parameters. Then 2 hours is the charging time, so we can calculate rate of charging reaction mixture 1 and the rate of charging for reaction mixture 2. Okay, so we can calculate that simply by dividing total quantity divided by 2 is the rate of charging. Okay, it is kg per hour. Then we can calculate the reaction rate of charging of reaction mixture 2 by simply dividing 2 hours as we have considered, and rate of charging for the limiting reagent, because the limiting reagent reactant. Okay, so we have to calculate based on that. It is the limiting reactant rate of charging. Okay, so we can Also, as I discussed, there is the uh, one product and one byproduct formation. So here we molecular weight of product, and we have molecular weight of byproduct, that is HCl. So we calculate for HCl molecular weight is 36.5 and for the product is 381.2, as I have taken from the data available with me. So we can calculate rate of product generation and the byproduct generation. So calculate rate of product generation, we need to divide molecular weight of product divided by molecular weight of reactant 1 into rate of charging. Okay, molecular weight of reactant 1 and the rate of charging is the uh, limiting reagent rate of charging. So we will get the calculated, so we will get the rate of product generations. In same way we can calculate rate of HCl generation. Okay, how much quantity of HCl is generated. So for the HCl generation calculations, we can divide this simply by molecular weight of HCl divided by molecular weight of mixture 1 into the quantity of the reactant, limiting reactant charging. So this is the kg per hour rate of HCl generation. Okay, so now we can convert that into rate of product generation in kilomole. Okay, generation in kilomole, and same for the rate of byproduct generation, which is HCl. Okay, generation in kilomole. So to calculate that, we can simply divide this with the molecular weight of the product. Okay, so we got that much of kilomole for the products, and we got similar way rate of HCl generation divided by the molecular weight of HCl. So we got the rate of HCl generation in kilomole. Okay, so now we can check the total product generation. Okay, this is the total product generation. Simply calculate this, as we have considered the total reaction time 2. So total reaction product generation is the rate of generation into reaction hours. That means ki total 3086 kg of product generation, and same for the total HCl generation. We can check by the calculations the rate of HCl generation here into the reaction time. So we'll get the total HCl generation in this case. Okay, so we got the total HCl generation and the total byproduct generation and product generation. So we simply check it, total kilomole mole of product and the total kilomole of byproduct, that is HCl generation. So we can simply do this by dividing its molecular weight. Okay, so here we got the total number of moles, and same is case for the HCl generation. We have to divide the total HCl generated divided by the molecular weight. So we got the total mole of HCl generation during the reaction. Okay, so now we can simply put the density of the material, density of reaction material 1, density of reaction material 2, and same for the, we can check for the density of product and density of the byproduct. Okay, so these required for the calculations, so we can simply put it here, density in whatever the available kg per meter cube, and here also kg per meter cube. Okay, so now we have to check the, like, reactor nominal volume, which is 12.5 kl, then the reactor gross volume, which is 14.5 kl. Okay, so we have the mass. Here we can calculate the total volume of reaction mixture, which is 10,000, divided by density of that reaction mixture, material 1. Okay, that much of KL we have volume. So we can calculate volume of reactors after 1 hour. Volume of reactor in 1 hour of material charging. So we can calculate simply this by the rate of feed materials equals into the divided by the its density, so we get that into meter cube, and simply plus the whatever the reactant 1 we charged, so we got the total volume available in the reactor. So simply we have calculated the volume of reactors, and we can check the empty space here by simply multiply minus the total volume minus the whatever the occupancy of reactors. Okay, so now we can use the ideal gas equations to calculate the max pressure. PV is equal to nRT. The based on this equation, we have simply take it the universal gas constant R here, then the temperature is, which is the reaction mass temperature. So to calculate the max pressure, we simply turn the number of moles into universal gas constant R into temperature divided by the volume of the reactants. Simply it is like PV is equal to nRT. Okay, n into R into T. So we got the max pressure rise in 2 hours. Hope you got the clarity how to calculate the any of the process whenever you are doing the HAZOB or any process safety studies. You need to calculate such a scenario where your pressure built up scenario will occurs in case of vent block. So using this you can simply calculate Excel template or Excel spreadsheet you can use to calculate this, whatever the limiting reagents and the which component is contributing for the pressure rise in such a scenario. So hope you got the clarity. You can practice it with your the actual scenarios or actual process conditions whichever available with you. So here I can't write down the material specs, hence I just simply puts down the its molecular weights and the reaction mixture 1 and reaction mixture 2 and product. So hope you'll understood this, and if you like, please subscribe our channel and drop me a comment if any doubts. Thank you for now. Bye bye.